Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's a great pleasure to introduce Subhasish Mitra, who is an assistant professor at Stanford. Subhasish was with Intel before he joined Stanford. He was a principal engineer over there. He worked for 5 years. And he's developed very influential techniques in robust system design. He worked on from the circuit level to the system level. In particular, he's developed a test compression technique, XCompact at Intel, which received the Intel Achievement Award, which is the highest honors at Intel, technical honors, let me say. And he's been working on built-in software resilience techniques. I think he will talk a little bit about that, and online self-test techniques. And with that,
thank you very much, Honor, for inviting me over here. And actually, we are having a very good collaboration going on. My student Tianjing is sitting over here. She's actually spending doing her internship at MSR this summer. So hopefully, there will be a lot of interest in this kind of stuff. And I would like to have a two-way conversation rather than a one-way traffic over here. So please feel free to stop me and ask questions. That way, it will be more fun. So let's say that you designed a system, and let's say we start from a hardware chip, and we perfectly made sure that everything was correct. It was perfectly formally verified, and then it was tested right, so there were no defects. And you have this chip in the field, and then you see errors happening left and right in the storage nodes, in the flip-flops, in the memories, in the combinational logic. And one of the big sources of these problems is what is called these radiation-induced soft errors that happen because of alpha particles in the packaging material and neutrons that are coming from cosmic rays, basically. Okay, so the point over here is that in the past, no one used to care about these kinds of problems. Only the space guys used to worry about these radiation-induced soft errors. But going forward at sub-45 nanometer technologies, as we will see on the next slide, you have to worry about almost all parts of your design and its resilience to soft errors. You have to worry about memories, you have to worry about flip-flops, you have to worry about probably combinational logic as well, although it's not quite clear that whether combinational logic is going to play a big role or not. But this is a big problem that one has to worry about. And here is a quote from one of the IT executives, and this came up in the Forbes magazine a couple years back in response to one of the processors that were built and sold to these guys. So who cares about soft errors? Why are we talking about it? Well, it all depends on error rates. And I'm not going to get into the details of where I got this number from. But you will roughly find, if you look at soft error rates of individual components in a system, you will get a number of something like this, that if you had a 20,000 processor server farm, you will have one major flip-flop error every 20 days. Now, this is to say that you could have a big problem as a result of this or not. So, for example, here is an actual chip that I worked on in the past. And if you look at the various components of this chip, you worry about memories, you worry about flip-flops, you worry about combinational logic, and you worry about the contributions of these various components to the overall soft error rate of this chip. And this is what you find. For example, this particular chip, it was a storage chip, and it had a lot of on-chip memories. And those on-chip memories will be typically protected using ECC, error correcting codes. Still, there were lots of on-chip memories that were not protected, or the designers decided not to protect those on-chip memories because every chip at the end of the day has to satisfy a certain soft error rate goal. Almost no chip has a zero soft error rate. As long as you satisfy your goal that your customer wants, you are okay. For that particular chip, it was fine not to protect this on-chip, this remaining unprotected memory that's shown over here. But that's not what the biggest concern was at that time. The concern was that how in the world are we going to deal with these flip-flops that had almost the same chunk, if you look at, of the overall soft error rate contribution as the unprotected memory. Because for the unprotected memory, if one had to go and put more protection in, one would have to go and put more ECC or put more error correcting codes. There was a path that was known to be able to solve that problem, versus for flip-flops, you cannot use ECC, and the question is, what else could you do? And that was one of the burning questions at that time. So going back to my previous point of who cares about soft errors, as we said over here, that if you had a 20,000 processors server farm, you could have roughly one major flip-flop error every 20 days. And this measure, it has a meaning. So people have done these studies where they have shown that most soft errors do not matter at a system level. It's only roughly around 5% of the soft errors that really matter at the system level. And people do not agree. Some say 10%, some say 1%, some say 5%. It doesn't really matter, because these 20 days could become 200 days, or it could become 4 days, or whatever. Those are all very important numbers from our standpoint. And what are these major effects could be? Well, one of the major effects could be silent data corruption, which means that one would go to the bank and deposit $20,000, and depending on which way the bit flipped, you could either be very happy or you could be very sad. And so that's really a big issue, and that's why almost every chip today has two soft error rate goals, one about the silent data corruption, and they want to have very low rates of silent data corruption goals. Versus when you look at detected but uncorrected errors, which means that that there is a problem in your system, but you really do not know how to deal with it, which means that either you have to do some kind of a recovery or something, and depending on how recovery is implemented, you could have system downtime or not. And we know, I do not have to preach this to this audience, that the cost of downtime could be really high. So again, it's not that you have to worry about these silent errors. You also have to worry about detected but uncorrectable errors and do something about them. And since I'm an academic, wearing my academic hat, I just said memory soft errors is a solved problem. That's not really true. There are lots of open issues that we could discuss. But at a bigger scale, I think these are much more open problems than memory soft errors. So taking a step back, these soft errors are not the only problems that we have to worry about going forward. Now, if you look at some of the technology-related problems, you have to worry about radiation for sure, the soft errors that we were talking about. You have to worry about this phenomena which is called erratic bits. And this erratic bits, actually Intel had a paper in IEDM in 2005 that kind of was one of the first papers that talked about these erratic bits. But they found that for their really low power processors, they found that the minimum voltage at which the memories could work were erratically shifting over time. Which means that one way to solve the problem is to have a big voltage guard band, to say, well, my Vmin is going to go up. Now these are targeted for really low power applications, and then your battery life is affected. And people were really concerned about a problem like this. So, but these are kind of the sources of temporary errors. Versus going forward, you also have to worry about these other sources of problems, which include aging. Transistors are like human beings, and they age over time, and the amount of aging depends on how much workload these transistors were working on. You have to worry about early life failures. Typically what happens is when chips are designed and tested, in the test floor, these chips are stressed at a very high voltage and at a high temperature, so that the weak chips are screened out. Now if you test these chips too much, for example, if you stress them too much, this is what happens to the chips. And this was actually one of the highest performance microprocessor chips from a company, not Intel, because I used to work at Intel. So, and you can see that basically what happened is, because of extremely high leakage currents in the burn-in oven at a higher temperature, these chips actually were fried. So which means that either you can apply a lot of stress, which will kill your good chips, or you're going to apply very little stress, which won't be enough to stress your bad chips, which means now you have to do something about the so-called early life failures. Otherwise, these chips will fail within the warranty period, and the vendor has to deal with it. And of course, you have to worry about process variations. And I'm sure you heard about process variations a lot. And so, that's kind of the last one on my list, although, it could be something very important. These are the ones that are not talked about a whole lot, but these are some of the mechanisms that people are worried about going forward. So how do we deal with these problems? Well, what we think at Stanford in our research group, what we think is that to be able to deal with the problems of these soft errors and erratic bits, you will use a technique which is called BISER, or built-in software resilience, that I will talk about today. And this BISER technique is going to correct all these temporary errors that you would worry about. And then for the two sides of the bathtub curve that have to do with early life failures, as I said, that burn-in is getting difficult, and almost any other alternatives to burn-in that the industry developed in the 80s are in their sunset boulevard right now, because none of them work, because everybody is reaching their limits basically, and IDDQ is an example of that. So for these early life failures and for aging problems, you will be using a technique that I will also talk about, which is called circuit failure prediction, where you will be collecting a lot of data while the system is running, and based on that data you will try to tell that where the system is actually going and whether it could fail because of these aging problems. And to be able to do a good prediction, you may have to do a very thorough online self-test, because we know that as with any prediction, if the input data is not good enough, then your prediction won't be very good. So that's why you may want to do a very thorough online self-test. But given this circuit failure prediction together with online self-test, we think that that can resolve the problems of early life failures and wear out and aging and so on. Yes?
What's the time frame for wear out?
So in the past, people used to worry about wear out, like really late in the game. For example, like 20 years or 15 years or something like that. So today, what has happened is that wear out happens from day zero. So for example, if you have a chip and your PMOS transistors, for example, their threshold voltages will be degrading, just from the day that you were, exercising the chip. Now, one way to deal with the problem is to say that, well, if my speed as a result changed by 5%, let's say over 5 years, I'm just making these numbers up, then you may not worry about it, because you could say, well, I would just put a guard band of 5% in my frequency, and I could claim that I do not have an aging problem. Although there is an aging problem that's going on that has been resolved by doing pessimistic design. Now, there is a big worry going forward that if you were at least making these chips work for 7 years or something like that, which would be the case for enterprise applications, and you could have as much as 20% of the guard band being, you may have to go and put in 20% of the guard band to deal with the problem. Now that becomes a very important issue, because as we know very well that our speeds are not going up, number one. Number two, our variations are going up, which means that you have to put a guard band for variations, and then now you have to go and put a guard band for aging, and you put on guard bands over guard bands over guard bands, and how many guard bands you're going to put basically. So that's where the worry is. So it depends on how you look at the problem of aging. Does that answer your question?
I'm curious about if I buy a computer today, sort of, is there a warranty on how long the processor will run?
Yes, roughly. So there are two kinds of warranties. So there is one kind of warranty today that when you buy a processor, that if it fails, if it breaks within the warranty period completely, then somebody is going to replace your processor. And that warranty makes sense today is because people are still doing this burn-in, and since they're doing burn-in, most of the weak chips they have they're gone in the manufacturing floor. So you may like maybe they will have some goals like 100 in a million or 50 in a million like could be bad because of that thing. So that's one kind of warranty. And the other kind of warranty is basically, it's not really a warranty, but it's more like a use condition thing, which says that if you buy a PC, maybe you use a PC for only 3 years, or in 5 years, I do not, maybe probably 3 years is probably the right number. And if you use it for 3 years, they will at least try to target by design and by guard banding that you get a certain level of speed by doing something like that. Now that's becoming very murky because our speeds are not even constant anymore inside CPUs because of dynamic voltage and frequency scaling and so on. So it's not clear cut, but at least they try to target when they say that this thing is going to work at certain gigahertz as a speed bin, they take those speed guardbands into account today.
So I shouldn't be surprised if after 7 years,
oh yes,
my
absolutely,
computer either breaks or
absolutely.
is running slow.
So that's the whole reason, for the people that do overclocking to play games, they do not go and so that's why they are going to now have even tags, isn't it, inside the processor or something to find out if this was overclocked or not, and then they are not going to replace your processor. If you came back after 2 years and they found that you overclocked it, it has to do with reliability basically. That's it. That's aging basically. So what we think is that by using this concept of BISER and circuit failure prediction and online self-test, we can have a consistent story about a new way of thinking about designing robust systems. Kind of it's a departure from the classical thinking of having a massive redundancy or massive online checking to be able to deal with the problems, but more like understanding the underlying physics of these mechanisms to come up with very optimized solutions. And hopefully I'll be able to convince you that the costs of doing that will be much cheaper than just relying on redundancy to be able to solve some of these problems. Now, to be able to do that, the reason that I came here and the reason Honor got so interested in it and we were doing this collaboration is what is most important is this global optimization, because I will go and I will put a lot of bells and whistles inside the hardware to be able to do some of these problems, but then you need optimization at higher levels of the stack to be able to orchestrate my hardware mechanisms the right way at the right time, so that you do not pay a full very high system level cost. So the story about cutting down the cost is going to be in this global optimization, and hopefully I'll be able to show you some examples of how that would happen. So that's why it is important for folks like yourselves to be interested in these kinds of problems. So that's the story about technology, and I'm sure you have heard people saying that, oh gee, these are never going to be problems anymore because everybody is going to stop at 22 nanometers and the semiconductor industry is not going to go beyond 22 nanometers. So what I tell my students and and everybody, that still actually we are in business so far as our research group is concerned, because even if you do not worry about technology related problems that we talked about before, still even if we stop at 22 nanometers, still we'll be building complex systems. And if we build complex systems, that means that we have to deal with the problems of bugs. And validation will still continue to be a problem. And if you look at hardware design today, hardware design is mostly about validation today. And even in validation, what people have found is that while significant progress has been made in pre-silicon validation, which is often called verification, where people use this simulation-based verification, formal verification, and so on, what people are finding is post-silicon validation is one of the big costs in hardware design today. And by post-silicon validation, what we mean is the chip came back, you plugged into the system, and what you saw is a blue screen. And from there, you have to find out which one of those billion transistors is actually malfunctioning, because it just takes only one logic gate to malfunction in a synchronous design to be able to create any problem at the lower level, at one level up. So from that level, how do you find out? Yes?
So when you say a gate is malfunctioning, you don't mean it's because of a logic error, it's because of some
timing shifts. Yeah, absolutely. Yeah. So it could be, yeah. Actually, it's good if it is a logic error, okay? Because if it is logic error, then it will be repeatable, okay? Now, if it was a timing error because some noise happened or because a slight variation happened, those are like what are called Heisenbugs, which means that when you try to observe when the problem happened, the problem is not going to happen. It's only in a certain electrical state of your system the problem is going to show up, and it will be extremely hard to reproduce. This is like, the car shows up a problem in the freeway, we go to the mechanic, and the mechanic says, no, there is no problem, everything is just fine. And they're saying it, and that's where the biggest cost is. They're saying that today it could be up to 35 to 40% of the total cost is about this. And in the future, I have a quote from an Intel executive later on in my talk, which says that this will exceed design cost unless we do something about it. So, we are in business. And even if the technology stops, and we have a technique called IFRA, actually, which can go and actually do this thing. From a system level failure, you can tell that you can kind of pinpoint that whether it's the ALU or the scheduler or something in the hardware that's creating the problem, and we can do it very efficiently. And I won't get into details of that, I'll just mention it later, but if anybody is interested, I'll talk about it.
How do you do it?
I can talk to you.
You're doing some machine learning stuff there?
Not really machine learning, but it is about data collection. So I do collect some very specific kind of data based on the architectural specific kind of data, and I do post-analysis of that in some clever ways, and I'll be very happy to talk about that. So I'm around today, and you can reach me later on. Please feel free. Yes.
Expand the acronym IFRA.
Yeah, IFRA stands for Instruction, Footprint, Recording, and Analysis. Yeah, which makes sense, isn't it? When instructions are passing through the processor, they have some footprints that you collect, and you have to be very, very careful about what kinds of footprints those are, and you record them concurrently. You do not do anything about it, and when a crash happens, you scan them out and you analyze them to find, to diagnose the failing locations.
Scanning and observation is happening in hardware.
Yes.
You store all this data in hardware buffers?
Only 60 kilobytes of hardware buffers. Not everything. You're not going to be able to store billions of instructions, isn't it?
Yes,
Now, of course. But then that's why what is very important is that you have to reduce your time from the occurrence of the problem to the time of the exposure of the problem to one level up, and that's where we play some tricks to cut down that time to be able to do that. And actually we have some actual demonstrations that it works in real life. So I'll be very happy to talk about it. Okay, so that kind of is a big picture. There is another project that we work on that I'll show 2 slides on, which is blue sky. We are even looking at beyond CMOS, and actually we showed the first experimental demonstration of being able to create complex logic gates out of carbon nanotube field effect transistors. And I'll share some pictures with you later on, but that's like really blue sky, but it's a lot of fun. Okay, so let's go back and let's get into the details. First I'll start with this built-in software resilience technique, and I'll show you how we can self-correct this radiation-induced soft errors. So here is a big picture. Here is the key takeaway of all this BISER stuff. If you look at traditional error detection and recovery, number one, it is expensive, and number two, it is expensive not only in terms of hardware cost, it's also expensive in terms of design methodology. I know of at least one microprocessor where people very seriously thought of implementing error detection and recovery, and later on backed off just because of the nightmare of validating that the recovery mechanism will actually recover the way you want it to recover at the right time. And that validation is very expensive. Versus this built-in software resilience that I will talk about, you will see that I'm going to redesign the flip-flops inside any digital design, and that redesign of the flip-flops will self-correct any errors that would happen. Okay, and as we will see that it is you will be able to correct both errors in latches and combinational logic. Although just for being high level, I will focus on latches so that you get the essence of it, and I'll be very happy to talk about how one could do it for combinational logic as well. And very recently we showed that these are useful not only just for this radiation-induced soft errors, but also those erratic bit errors that I was talking about, these erratic shifts in V-min and so on. So my message is that, correct errors, don't detect them. So here is how it works. So let's say that you got a combinational logic, and this will be at the logic level. This won't be too many transistors. This is the only one transistor diagram that I have in my presentation, so so please don't worry about it. So let's say you have a combinational logic, and the output of the combinational logic is connected to a latch, not a flip-flop, latch. Okay, suppose you could do the same thing for flip-flops, and suppose that I gave you another latch in parallel to this latch. Just take my word today, okay, and I'll talk about where this latch comes from and what's the cost and all that kind of stuff. So one thing that you could do, of course, to say that, well, I'll connect the output of this combinational logic to this latch, and I'll connect the output of the combinational logic to this latch. Of course I could do that. And then you could say, well, now that I have these two latches, I could stick in a comparator, for example, and if there was an error, there will be an error flag which says that you got an error. Now that's not a very good idea. The reason it's not a very good idea is the following, that now you think of a design with 1 million latches, and each of those latches will be holding an error signal saying that, oh, whether I found an error or not. Now to be able to do any kind of a recovery, you have to grab all those error signals and you have to pass them on to your recovery block to tell the recovery block that, now you have to do recovery. And suddenly your chip design will be dominated by all the routing of those error signals that will have to go to the recovery block. And the designers will just hate you because routing is already a big problem, and this add speed routing of error signals, they will say, I'd rather stay with the old technology and not deal with it. So instead of doing that, what you do is you just insert this transistor structure with 4 transistors. And this is actually a very well-known structure that was actually invented by Mueller in 1959 at the University of Illinois. Okay? And this is called a C element that people have used extensively in asynchronous circuit design. And this C element works in the following way. So when the 2 inputs of the C element are the same, it acts as an inverter. So for example, you can see that these are A's and B's, 0, 0, 1, 1, it acts as an inverter. When the 2 inputs of the C element are different, it holds the previous value at its output. So let's look at what happens over here. So if you didn't have any errors in these 2 latches, then the 2 inputs of the C element will be the same, it will act as an inverter, logically it will do the right thing, now electrically it will add some more load and so on, and you have to deal with it. Okay? Now if the 2 inputs of the C element are different, which means if one of these latches have an error, it will mismatch over here and the C element will retain the previous value at its output. Now who in the world has said that this previous value is the correct value? Because if the previous value is not the correct value, I have not done anything good by having this C element, isn't it? And why am I calling it a self-correcting design? So on the next slide, using cartoon animation, I will formally prove that the previous value will always be the correct value actually. And that's why it will work. Okay? And here is how it works. So again, you have these 2 latches. This is the system latch, this is the redundant latch. And your combinational logic is going to write something into the latches. So the way this whole thing works is the following, as we all know, that first, let's say the combinational logic was trying to write a 0 into these 2 latches. We know that the clock input of these latches have to be 1. That's when the latches are in transparent mode. That's when you can write into the latches. Now, the key observation is that this is very well known in software literature, that when the latches are transparent, they are not vulnerable to soft errors, because the latches are being very strongly driven by the upstream combinational logic. So what happens is, this 0 got written over here, this acted as an inverter, you got a 1 at the output, which is the inverted output. And now the clock input went from 1 to 0, that's when the latches are actually storing the value, and that's when you're worried about soft errors inside the latches. A flip happens, let's say on this latch, doesn't really matter, it could be any one of these latches. The C element sees a mismatch at its 2 inputs and it's going to block, and the output continues to stay at the correct value. By taking advantage of this fact, you can show that it is a self-correcting design because it retains the correct value at its output no matter what happens. Okay?
The trick was that you thought that you actually split it into two pieces, 2 phases.
Yes.
And you made this observation that the error happened only
in the second phase. If the error happened in the first phase, there would be no way you could help me. So, the way I think about it is that, it's always what I have found in most of the problems that I worked on, that, as soon as we go 1 level deep and we understand kind of the source of the issue, like that's where physics comes in. We understand the physics little bit, there are so many interesting solutions that one can come up with without having to pay that much price. If I didn't use that particular property, then everything will blow off, and a scheme like this would not work.
So there's also this hidden assumption that both cannot go back.
Oh, I'll talk about that. Yes. So there is an issue that what happens with single event multiple upsets, and I'll share some data with you, real data with you on what is the vulnerability of that. So you can think of this as a flip-flop. So now you can think of, for example, when people do design, they have a technology library, and the library has AND gates, OR gates, NAND gates. They have a regular flip-flop, they have a scan flip-flop. Now you think of having a BISER flip-flop inside your library basically. Now, so far as the cost is concerned, you will be thinking, well, what are the costs of doing something like this? That's what I'm going to share on the next slide, and then I'll try to share some really recent data that, I think I did a miracle by making some people agree that I can share this data with people. And yeah, go ahead.
What about an error in the C element?
Right. That's a very good question. So let's try to understand. What happens if there is an error in the C element? Well, if there is an error in the C element, these two latches, under a single error assumption, these two latches are going to drive the C element very strongly. So that's why what you will see is that the maximum you will see a glitch at the output of the C element. And that glitch will go away in the subsequent stages of the combinational logic. But very good question. So please ask these questions. Otherwise, it's very hard to talk about everything. Okay, but good. I'm making people think. So what's the cost of doing something like this? So of course, at the flip-flop level. So let's look at power cost first, because that's what people care about the most. And then we'll talk about area costs. So at the flip-flop level, I got two latches that are transitioning. So of course, I'm going to have 2x the power at the flip-flop level. I cannot do anything about it. But again, nobody sells flip-flops in an actual design. Everybody sells a full design. So we looked at the alpha processor because it was open source, and we got hold of this error injector that Professor Sanjay Patel at Illinois developed. And based on that, we found that if you can find the right flip-flops to protect, not all flip-flops are equally important from a architectural level error standpoint. So if you can find the right flip-flops to protect, for example, if you wanted to reduce your chip level software rate by 2x, you just protect 2% of the flip-flops, 15% of the flip-flops with a 2% power penalty. If you wanted to cut down the chip level software rate by 10x, you protect around 50% of the flip-flops, 50% of the important flip-flops, and you pay a 9% chip level power penalty of doing something like this. Yes.
So you predict the important ones by injecting faults and determining.
Here we were injecting errors, doing a fault injection and determining whether it was important or not. Either on the next slide or 2 slides from here, I will show you a formal verification technique for doing that actually. So because that's an important question now. That's where optimization now comes in. Given that we can solve the problem at the lowest level to be able to contain cost, now we have to look at other layers to be able to cut down, to be able to do the cost optimization. So this is what you see. Now, what are the chip level area costs of doing something like this? Well, of course, at a flip-flop level, your area doubles because your flip-flop has gotten bigger. But then there are 2 benefits that work in your favor. Number 1, we know that in VLSI design, you are always dominated by long interconnects. Versus here, what you are adding is local transistors and local interconnects. And we have done these experiments, place and route and everything. My friends at various other companies have done these experiments. And the chip level area cost of doing something like this is extremely small. Sometimes you see a 1%, sometimes you see a 0.5%, sometimes even people have seen 0%. Because their chips had so much white space because these were synthesized designs rather than hand-placed custom designs. And you can use the next question is, how do you really optimize the BISER insertion, basically the question that you were asking. There is actually another benefit of using these BISER flip-flops in post-silicon validation and test that I'll talk about later. So let's focus on, this is the thing that I was talking about, how do you go and find out which flip-flops are the most important flip-flops? Of course, you could do a lot of fault injections or error injections to be able to do that. The thing with error injection is that if error injection tells you that there is a problem, that's a good news because then you know that there is a problem. If error injection tells you that there is no problem, the trouble is you really do not know whether there is no problem or whether it's simply because that you have a coverage issue over here. Okay, so that's where actually this is joint work with Professor Sanjit Seshia at UC Berkeley, where we were using a formal verification approach of doing it. We were saying that, look, what's going on over here? So if you have a bunch of flip-flops, and let's say you were worried about a soft error in a flip-flop, you could model that as a 2-state finite state machine. So there was no soft error to start with. At some arbitrary cycle, a soft error happened, and from that standpoint, there is no other soft error that would happen. Everything would be fine with that flip-flop. And now, if you just take a cross product of this particular 2-state machine with the formal model of your design, and then you can check for properties of the design, and then you could come up with 2 answers. If the properties pass, then you don't have to protect that flip-flop. Otherwise, if the properties do not pass, you do have to protect the flip-flop, basically. And and you can use a model checker and so on, and we did it. What you find is that by doing this, for example, for the space-wire communication protocol chip design, which is on open course, you can cut down the power cost of BISER by 4x. So it's like something around 5% or something like that at the chip level that you have to pay the price. It's a rigorous way of really proving that you can actually do it. But of course,
But this is kind of bizarre. This is saying that there are some latches in there. It doesn't matter what values they have.
Yes.
What the hell are those latches doing?
Exactly. So that's a very good question. So what are they doing? Well, there are two things that you can take benefit of. First of all, since it was a communications protocol, there is already built-in mechanisms in the communication protocol itself to deal with errors. Okay. For example, if you have a CRC errors, or if you have a timeout errors, okay, they will automatically the system will deal with it. So that's why even if those latches, those are care bits, okay, but still, you do not have to go and protect them because they're taken care of at the system level, at the protocol level. But then there is another thing, which is that if you have a single cycle error in a latch, that's not equivalent to be a don't care. So there is this thing, isn't it, that if there is a stuck at fault in a particular design, that means if a signal is always stuck at 1, and if you cannot find it, which means it's a don't care. But in this particular case, it's a single cycle stuck at, which is different from saying that like that you don't care about the system. So I can show you actually finite state machine examples where you could have a single cycle error that would not matter, but if that particular flip-flop was gone, your complete design would be messed up.
But I thought even if you have a single cycle error, then because that can be repeated in every cycle, it's like you are completely existentially quantifying out the contents of that flip-flop.
Yeah, but then like you could always have architectural constraints, for example, like these are the sequential don't cares. You could say that every time I have a 1 over here, I have a 0 over there, okay? Something like that, okay? So if you have architectural constraints of of what you said would be true if there would be no constraint on the contents of the flip-flops. But if there are only a certain set of bits in the flip-flops that are care bits, the others are sequentially don't care bits, then you may run into a situation like that. But for this particular design, what we found was that we were taking advantage of basically the protocol level design, basically. That, yes.
So I have basically a comment about that also.
Yes.
So it seems that to save, so this BISER stuff is really cool because you do something local and
Thank
you
you.
fix the problem. Okay. But now you're trying to save that stuff.
Yes.
And you're trying to not use it.
Yes.
And then what you're going to do is if you don't use it, then you might trigger all this high-level protocol stuff,
Sure.
right? Which
Absolutely.
might have its own expense, right? Of course, nothing is for free.
Absolutely, yes. Yeah, I absolutely agree, and that's where that's why the optimization is so important to understand that at what level you want to go and solve the problem. I absolutely agree with you. Yes. There is also another issue, isn't it? You wanted to make a comment?
Well, also, I mean, if you make the reliability at the lower level stronger, then you can eliminate some of the protocol at the higher level. I mean, so
You could.
have to automate some
At the end of the
processes.
day, that's why it's so important to have a cross-layer optimization. Exactly. There is another issue, isn't it? Like which we did not even talk about. Who in the world said that we had the complete specification of that particular thing that you very.
Powerful, and we all know it's not all powerful.
But it's garbage in, garbage out, isn't it? Like if you didn't verify with respect to the right set of properties, it goes back to the coverage of your properties that I verified against. So, but here is the point that I wanted to make is that there are interesting techniques, and one could even think of, for example, combining error injection with something like this to be able to tell what you could do. This is kind of an interesting spin to the whole thing, whole problem. There is another benefit of using a technique like BISER that I was showing before, and the benefit is that actually you can turn protection on and off. So here is actually a flip-flop design that's inside many of your processors. This is Intel's scan flip-flop design, and Intel decided to implement a scan flip-flop in this particular way for the following reason, so that while the system is running, they could scan out the contents, which is a snapshot of the system, without having to stop the system. And this was very useful for Postsilicon validation purposes. And that's why they had this paired flip-flop. And now you can reuse the same thing for protection. And now, what I call it is a design quality flip-flop, okay? Because that's going to do software correction in the field. That's going to help for scan test on the tester floor. And then that's going to also enable you to do Postsilicon debug, in in a Postsilicon debug environment. And oh, by the way, since you can turn this flip-flop on and off, that means that you can have, again, if you understood your system well enough, you could be in between two modes. You could be in a high reliability mode, and you could be in an economy mode, where, yeah, the area you are stuck with, but area is not the biggest deal. The power is the biggest thing, where you can play games either statically or dynamically. Which brings to the question of application level error rates. So when I was at Intel, and it's not about Intel, it's with almost any company that you can think of, there was this whole issue of having one single core, one single processor core that will run for all applications, like for laptops, for servers, and so on. And then there are these wars, that who pays the price of reliability, because more power, more software rate protection, the goals could be very different depending on what market space you are talking about. By having this kind of a dynamic way of turning protection on and off, which we call reconfigurable protection, you can trade off. You can say, well, for applications that do not really care about soft errors, I turn the protection off, otherwise I turn the protection on, and the question is, are there any benefits of even doing it dynamically during runtime? I don't know the answer, so that's why these are question marks. But these are interesting things that are enabled by a flip-flop design like that.
So one thing in your design, because it's local, you don't actually know if it's happening.
Yes.
So have you thought at all about that? In other words,
you're not the first person who asked me the question, as you can guess. Okay, so I have two answers to this. Okay, my first answer is that why do you need to know if I can correct? Okay, there are so many things that happen inside a design. Do you know about everything? And too much knowledge is sometimes not very good. Okay. Yeah. But at the same time, one could come up with incarnations of these flip-flops, for example, where you could have error checkers as well, rather than just having the C element at a higher cost, of course. And there were some companies that were even suggesting something like that. So yeah, you could do that.
Have you thought at all about like a statistical error detection network? Because, for example, in the case you're talking about where we're reconfigurable, if you had an environment where you're seeing a lot of errors, you might want to turn on error protection.
Yes, exactly. You could clearly do something like that. Yes, and the good news is that unlike typical power shutdown mechanisms that take a lot of cycles to be in a power saving mode or in a regular mode, here actually you take 4 clock cycles to turn protection on and off, because you do it using scan-enable signals that are already present inside the chip. So somebody already asked this question of what happens for multiple upsets. Now, if I was giving this talk to you last year, I would have said, oh, no one cares about multiple upsets. It's all about single upsets. But what has happened is that these companies have actual data now to show that first of all, for memories it was known for a long time that you have single event multiple upsets. But they have started seeing single event multiple upsets in 45 nanometer for flip-flops now. And although the rate of upsets is much lower, so maybe it's like for 5% of the cases or maybe 1% of the cases you will see single event multiple upsets. So still I could say, well, I am okay with respect to 20x or something like that. On the next slide I have some actual data for BISER that I will share with you. But the big one is that the big comment is single error assumption is not clearly sufficient. And to be able to do analysis of single event multiple upsets, you have to worry about layout, you have to worry about technology CAD. And we are doing some work, and we think that the BISER can cut down even single event multiple upsets by more than 100x. Actually, it could be up to 300x. Because what happens is, to give you the heuristic explanation of why that would be the case, in BISER, first of all, the corresponding nodes only have to be upset to be able to create problem. Now you can play layout tricks where the corresponding nodes are far away, but the non-corresponding nodes are very close to each other. So still you end up having a compact layout, but the effects are kind of moved away. Yes?
So that's equivalent to bit interleaving in memory?
In some sense, you can think of it that way, but at a much finer scale. But you can think of it that way, yes. But I was amazed in July. I was at this small conference called IOLTS, or International Online Test Symposium. They asked me to give an invited talk on soft errors, and I show up there, give my talk, and the next speaker is Dr. Norbert Seifert from Intel, who I worked with when I was at Intel, and he stands up and he starts showing data on my BISER flip-flops. So it seems that there were some experiments that were done by some folks at a 45 nanometer on a test chip, and BISER was there basically, and it was radiated. You can see what they found. So I worked with Norbert. I said, can I create one slide that will be approved by you that I can show to people, and finally they came back and said yes, I could do something. So for alpha particles, they found that BISER cuts down soft error rates by more than 1000x. For neutrons, they found that BISER cuts down soft error rate by more than 100x. Actually, it's far more than 100x. I was told not to tell the exact number basically. And what was found is that BISER was very effective in correcting single event multiple upsets. And the reason is because, first of all, because of the diversity that I was talking about, and also what was happening is BISER doesn't have any self-regenerative feedback. It's not like, if you have an error, you make up for it and you feed the same thing back into the flip-flop. It's like kind of, feed forward kind of a design. And that's why, the single event multiple upset effects are very small in BISER, and so, when they were saying that, this is 100x and all that stuff, that, includes even single event multiple upsets. So that's something that I was very happy about. And of course, Norbert said that I have to write this mandatory thing that you could get more reduction at higher cost. Okay, and I would agree with that. Okay, so that's what I had to say about built-in software resilience or BISER. And now I'll move on to the next topic, which is about circuit failure prediction. So again, to remind you where we are, we said that for this normal operation you care about the soft errors and temporary errors and so on, and that's why you would be using this built-in software resilience. Versus for early life failures and wear out, you'll be using this idea that we are calling circuit failure prediction with this CASP online self-test. So let's look at what is circuit failure prediction. Well, the whole idea behind circuit failure prediction is to be able to predict failures before errors appear in system data and states. And this is in contrast to classical error detection, where you find a problem after errors have appeared in system data and states. Of course, for something like a soft error or radiation-induced error, you are not going to be able to predict because it's a pretty random phenomenon. But for transistor aging and early life failures that I was talking about before, there is a gradual degradation that's associated with these mechanisms. And this gradual degradation shows up as delay shifts. And since this shows up as delay shifts, you can go and predict, you can tell that where the system is going before it has actually failed. And what are the pros and cons of doing circuit failure prediction? Well, since you are finding errors before since you are finding problems before errors appear in system data and states, you do not have an issue of data corruption. You do not have an issue of being able to deal with very high error rates, and recovering from high error rates is a problem. And it enables very good self-diagnosis, because now you are collecting all this information over several billions of cycles that the system is running to be able to predict that whether something is going bad or not. So you know what the behavior of the system was before it actually failed, or before it actually went to a failure scenario. And that's why for these mechanisms of transistor aging and early life failures, because of this gradual degradation which results in delay shifts, because of this physical phenomena, you can go and predict failures before errors appear in system data and states. And by the way, Shakespeare explained several centuries back why circuit failure prediction is a good idea. So what is the applicability of circuit failure prediction? Well, as I said, it has to do with degradation. And degradation shows up as delay shifts. Now the conventional wisdom about delay shift is that a delay shift makes things slow, and you will see a lot of people talking about it. The startling thing that we found, and this is based on you can see several generations of test chips that we have been doing, where we have been measuring stuff. We found that these delay shifts do not have to be positive delay shifts in the sense that they do not have to slow things down. They actually can make things fast before things break. But still there are delay shifts. And as long as you can find delay shifts, you can tell that whether there is something wrong going on in your system before the system fails. Okay, so that's kind of the key idea over here. Now, as I said, that for transistor aging, it's pretty well established how these delay shifts happen, and these are positive delay shifts. Things get slow, basically. But for early life failures, like for example gate oxide problems, as I said that we have actual experimental data, and we are clearly saying that delay shifts can happen in both directions before the chip absolutely fails, basically. But still there are delay shifts, and if you can find delay shifts, you should be able to find whether there is a problem, and this can provide even several different kinds of alternatives to burn-in. Now, how am I going to do circuit failure prediction now? So that was very fuzzy, kind of like a very philosophical discussion that we had until now about that we should be able to do circuit failure prediction. Now the question is, what kind of support do I need on chip to be able to do this kind of prediction? And there are two ways to do it. One is concurrently with application execution, which means while the system is running, while your application is running, you have special, again, flip-flop designs, special sensors that would look at delay shifts and would try to find out whether there have been any delay shifts that happen inside the system. Or you could do it using a periodic online self-test, which means that the system is running as it is, and every so often you run a very thorough online self-test, and you find out what's going to happen with these delay shifts in system. And that even provides some cost savings opportunity, because you may not need these sensors and you may not need to pay the power or the area price of doing these sensors and so on, but still you can find delay shifts. So I will get into the details on the next few slides on how one could design some sensors like this, and how one could do this kind of online self-test. So let me be more concrete, and let me show you one concrete example of circuit failure prediction in the context of NBTI aging, where NBTI stands for negative bias temperature instability. It's an aging mechanism that started happening in PMOS transistors starting 90 nanometer became very prominent starting 90 nanometer technology. Basically what happens is that threshold voltage degrades over time, which means that the drive current goes down over time, which means that the PMOS delay goes up over time, basically. And the factors that determine the amount of aging, they're like human beings, so it depends on temperature, that depends on voltage, it depends on the workload, because it is related to the percentage of time that the PMOS transistor is on. So as we discussed before about speed guard bands and so on, so the current industrial practice to be able to deal with this transistor aging is basically a worst case guard band. You tell, well, if you want to use this thing for 7 years in an enterprise environment, this is the maximum amount of aging one could ever get based on the worst case workload, the worst case temperature, and the worst case voltage. And you say, well, I'm just going to go and put a speed guard band based on that. If that speed guard band was 2%, you would not worry about it, you would just go and put it. If that speed guard band is 20%, then you would worry about it and you want to be able to do something about it. And that's what the big worry is going forward, that whether we are going to have very large guard bands when you talk about a 15 nanometer technology or something like this. And I'll show you an example of how one could use this concept of circuit failure prediction to eliminate such worst case guard band. So here is how it works. So what you do is, to start with, you start off with a very small guard band. So for example, instead of working correctly for up to 7 years, you say, well, I want to work correctly for up to 1 day or 15 days or 10 days. Doesn't really matter, okay? You start off with a very small guard band, and during this 15 days, I will stick with 15 days because that sounds like a good number. And during this 15 days, what you do is, while the system is running, you find these delay shifts. And you find these delay shifts either using sensors or using online self-test or something like that. And then at the end of the 15 days, what you want to find out is whether I got enough aging in various parts of the chip or not. Since I can find delay shifts, I'll be able to tell how much aging I have gotten in various parts of the chip. And based on this aging information, either you will decide that you do not have to make any changes to your guard band, or you do not have to make any changes to your system, or you will be doing some kind of self-healing. And luckily, there are various different options that are available for self-healing. For example, you can go and change the body bias. Now body bias knob may go away when you go to a 32 nanometer technology or something like this, but still it's still a knob that one could use depending on the company where the processors are built. You could adjust VDD, or you could even adjust speed in a very fine-grained way. Or actually people have found that if you let these transistors to rest a little bit, then these transistors recover from their aging, which means that you could even use spare cores to run your tasks and let these transistors go to a spa and recover from aging and then again work fine after so many days or something like this. Now that means that you have to design flip-flops with built-in aging sensors to be able to find these delay shifts, or you have to use online self-test. And yes?
Devices age evenly across the chip because
No.
It seems like you could have a particular part of the chip that ages like
Absolutely yes.
that would determine the worst case.
Yes.
And you would still get pretty conservative guard band because most of your techniques are pretty coarse grained.
Right. So what will happen is that it depends on the granularity basically. It depends on your voltage domains. It depends on your body bias domains and so on. Yes, but you are stuck with it basically. Maybe in the future we can think of very fine-grained ways of doing this self-healing that I do not know of right now.
So is the variance pretty big across?
Yes, the variance is big across. Yes, and one could take advantage of that. Okay, so the costs of putting these sensors, so we'll have special flip-flops as I will show next with built-in aging sensors. As you can see again, the costs are very small for doing something like this. And oh, by the way, a lot of people have suggested using ring oscillators and so on to collect this aging data. That's not very scalable because ring oscillators, their activity factors are very different from the activity factors or the signal probabilities of your actual design, and they may not even show up the same way basically. So a ring oscillator may or may not age as much as your actual design. So what you want to do is you want your actual design to tell you how much it has aged, and that's what you can do with these circuit failure prediction techniques. So the big question is what kinds of aging sensors you will be using and how you will be doing an online self-test to be able to do this circuit failure prediction. So let's talk about these two things for the remaining part of this presentation and we'll be done. So again, the idea behind these sensors to find delay shifts is the following. That today, for example, let's say you had this guard band TG, the 15-day guard band that we were talking about. If you get the chip out of the door today, you know that all signals will transition before this TG today. But tomorrow, depending on the slack of your pads, depending on how much this chip has actually aged, these transitions may or may not creep into the guard band. And that is actually the signature that you can find using, for example, a special sensor that's designed inside the flip-flop to tell that the combinational logic that's connected at the output of this, at the input of this flip-flop, where its signals are transitioning with respect to that clock age. And basically that's what an aging sensor does. You have to make sure there are lots of details about this thing. You have to make sure that the aging sensor itself is aging resistant. You have to make sure that this aging sensor is not very big. You have to make sure, you have to be careful about where you optimize, and you do not want to place these aging sensors in all flip-flops of your design and so on. But I wanted to give an essence of this thing. I won't talk about those details. One important point to note is, again, you have made the flip-flops bigger, but you have not added any global interconnects because you'll be using the scan chain, which is already existing on the chip, to get the information out. And why is it possible? Well, I'll come to this point a little later, but let's go to that scan chain thing. Because it is a prediction technique, which means that you are taking advantage of the gradual degradation mechanism, so you do not have to get this information out that whether something has actually aged right at the cycle where you have captured that delay shift. You can wait for a while, and like 15 days we were talking about, when you can get that information out, which means that you do not really have to go and scan out, have at-speed interconnects to do this thing. You can use the existing scan chain to get the information out. You do not have to add any global interconnects. The other thing that people worry about a lot with these kinds of techniques is whether it imposes any additional hold time constraints in your design. There have been some work that have been done that imposes hold times, and hold times are not good. No one wants hold time issues because that can completely mess up your design. So, but techniques like this never impose any hold times. So, do these things work in real life? I was pretty high level about, like the details, but yes, these things do work in real life. There are actual test chips which show that these things are operational and they do the right thing. Now, as we said, that to be able to do a good circuit failure prediction, you have to apply a very thorough online self-test. And why? Because it could very well be that your application may not be exercising the paths that are aging, because it depends on the profiles of your application. And we know for any prediction mechanism, it's garbage in, garbage out. If you do not give good inputs, you're not going to get good prediction. And also, online self-test is also useful for hard failure detection and diagnosis. Now, there are some constraints about doing online self-test. First of all, since we are talking about delay shifts, now we are talking about very thorough delay tests. You cannot simply do some stuck at fault testing and say, well, I'm done. You have to do pretty thorough delay tests to be able to find these problems. Number one. Number two is when you do online self-test, you cannot have any visible system level downtime, because if the system is down, that's of no use. There should be minimal application level performance impact. That means you have to be clever about how you schedule these online self-tests. Of course, it has to be low cost, and of course, it has to have minimal design flow impact. Now, let's look at some of the existing techniques for online self-test, and they are inadequate. For example, you could think of logic built-in self-test, or LBIST, which I'm sure many of you are familiar with, at least heard about it. Logic built-in self-test has very low test coverage with respect to delay faults. You cannot get very high delay test coverage out of random patterns, basically, which logic built-in self-test uses. Cost can be very high, design flow can be really messy. So that's why people haven't even used logic built-in self-test in a big way, even for regular manufacturing tests. There is this idea from 1986 by Mel Brewer from USC on this idea called roving emulation. Basically, their idea was that, if I cast this idea in today's terms, basically what they were talking about is if you have a multi-cores, and if you have one spare core, and you always check your core under test with respect to that one core. So it's like a duplication, time multiplex duplication, basically. But that wasn't the idea that Mel Brewer was talking about that time. He was talking about an emulation engine, so that you can emulate almost anything. It's deeper than that. But I just gave a very high-level view. Again, the issue is that if you're talking about applications, we can already find about applications by finding those delay shifts. That's not the biggest problem. The whole reason of doing online self-test is very high coverage. And if you still rely on the application to give you the coverage, again, you do not know what you are getting. So you have to have very high coverage online self-tests, which these techniques cannot give. So what do? Well, you do something very simple and stupid, and that's what we call CASP. CASP stands for Concurrent, Autonomous, Stored Patterns. It's very simple. Concurrent, why? Because, well, like if you have multi-core systems, you can test one or more cores, while the rest of the cores are doing their job, which means that no visible system level downtime. Autonomous, because there will be an on-chip test controller, and that's almost the only thing that you have to implement to be able to do something like this. So no one has to use a tester or do this thing manually. And third is the most funniest thing, which is that you can just go and store all your test patterns that you could think of in an off-chip flash, and that will be it. And you can store whatever test patterns you want, and you can store all your production tests, your structural and functional tests with quantified coverage and so on, and and you will get a really good test coverage which you could not get with built-in self-test. And why does this make sense today? This sounds like a trivial and stupid idea. Why does it make sense today? Well, in the past, people could not think of an idea like this because the cost of non-volatile storage was so much. But today, just having an off-chip flash to be able to store these test patterns is nothing, and the amount of storage we are talking about is, okay, like I will show you some results for the Sun's Niagara OpenSpark. You will find it's like 6 megabytes of storage or something like this. Okay, I give you a gigabyte. Okay, still it's nothing compared to the amount of non-volatile storage that I am getting. So that's why the major technology trends favored this idea. This is the classic example of some things that did not make any sense 10 years back. But with the technology trends changing, we should not think about these complex ways of solving the problem. There are far simpler ways of solving this problem. So what we do, multi-core designs, allows concurrent online self-test, and that's what basically Yanjing, is working on over here, at MSR, on doing very optimized schedulers basically for running these online self-tests. And then we go and store all our test patterns in low-cost non-volatile storage. It's also very flexible and upgradable in the field. After your system is in the field, if you find that a specific kind of failure mechanism is more prevalent than the other, you can go and change your test patterns, because Microsoft people are very good at helping people download patches. Now you can go and download test pattern patches basically while the system is running, based on what kind of failure mechanisms you see. And the big reason why this has been enabled today is because two things happen in the testing world that people sometimes do not know about. One is this idea of test compression, which can cut down the test data volume and test time by 10x to 100x to up to 1000x. And now if we can do this massive test compression, we do not need as much storage, we do not need as much test time to run these tests. And also another trend that's happening in the testing world is on-chip support for at-speed tests. In the past, people used to run tests out of the testers. But then, when you have a 2 gigahertz microprocessor, which is installed on a 500 megahertz tester, there is no way you can do at-speed tests from the tester. So you need on-chip support to be able to run at-speed tests. And if we have this on-chip support to run these at-speed tests, we should make use of them in the system to run these online tests. And that's why it becomes more and more relevant. You had a question?
Hardware built into the chip?
Yes.
Yeah.
So these are basically some funny ways of doing XOR gates. And if you do the XOR, so these are not your regular compression algorithms, okay? They do not work, okay? But these are some funny connections of XOR gates which kind of go back to coding theory actually. It gives rise to a new class of error correcting codes actually. And if you do that, you can cut down your test data volume very significantly without impacting test quality. And if you're interested, that's another talk, but then I can tell you in more details. That's like something very close to my heart. So we looked at actually, Yanjing did this work. We looked at the CASP for the OpenSpark T1 because it's open source. And if I show numbers, you won't be able to tell that now, this is some academic speaking, this is a real design. As you can see that even if you have a 10x compression, you're talking about 6 megabytes of storage, which is nothing, isn't it? Look at the extremely high coverages that we are getting. This true time is basically the most thorough delay test that the test community knows today. And getting a 93% of this true time coverage is extremely high. People do not get that in real life, but this is a real design. And the test time per core is roughly around 300 milliseconds. And this includes, this is assuming a flash. If you were having a hard disk, this number would go up. Assuming a flash, this includes the time to bring in the patterns, run the tests, compare the results, and and telling whether this chip works or not. And look, all this happens with an extremely small area impact of 0.01%. And Yanjing had to change 10,000 lines of Verilog code of this OpenSpark microprocessor to be able to implement something like that. So this is something very doable, something very practical. And this is how it works. So for example, there is a test scheduler which says, well, the core 4 is now selected for testing, core 4 is temporarily isolated, the test is run post-processing, and this continues to happen. And as you have, I'm sure you have all guessed that this scheduler is very important because the scheduler can completely mess up your entire application performance if you are not careful about what was running and if you are not careful about the scheduling. Actually, once you have this kind of an idea of this online self-test, you can make use of virtualization to optimize your online self-test. And the reason is the following, that if you wanted to implement the whole thing in hardware, you will run into a problem. And the problem is the following, let's say one of the cores is being tested. While it is being tested, the rest of the cores are running, and they may be generating requests for this core which is under test. And now you will need these buffers to store these requests, to buffer these requests. And you would not know how many buffers you would need to buffer these requests. Instead, if you have a virtualization support, you could either stall and you can bring it back, Or if you had a spare core, you could even transfer the activities on a core which is to be tested into that spare core and rove around while the rest of the system is seeing the constant number of cores. So you could do all that stuff, and we have been able to do this on an actual platform over here, which is shown over here. And you could have application performance impact of less than 2% if you had a spare core, for example, and rove things around. And you could do even better things. That's what Yanjing is working on scheduling techniques, so that you may not even need that spare core, for example, and still continue to do your work. Okay, so I'm almost done. Now I'll talk about some of the other research projects very quickly before I end this talk. But again, please feel free to stop me and ask questions. The first one is about post-silicon validation. I promise that I will show some slides. So as I said over here, this is a typical development flow for almost anything, and post-silicon validation cost is one of the biggest costs. And this is, Siva, he's the vice president of design technology solutions at Intel. This is, like what he said. And these are the numbers that are in published literature about today's post-silicon validation costs, and everybody thinks that this is going to go up. And the major causes of this cost are two. As we talked about, one is localization, and the other are these electrical bugs. And this is an actual number that I got from actual people that do actual post-silicon validation at these companies, that one electrical bug, it could take days to weeks to localize an electrical bug before the circuit debug guys come in and can fix it. Okay. So what we do is that in this IFRA, which stands for Instruction Footprint Recording and Analysis, it works mainly for processors right now. And the reason it works for processors is because the way we choose these instruction footprints, the way we choose this analysis, they are very tied to the microarchitecture of a processor. But if you can do that, you can eliminate the limitations of existing techniques, because you do not need any full system level reproducibility. You do not need any full system level simulation. But still, with 96% accuracy, you can tell the location of a bug. And by accuracy, I mean that you can tell which unit, which hardware block it came from, and the size of the block would be something like around 5,000 to 10,000 two input NAND gates, which is a pretty good granularity, because now the circuit level debug guys can go and test the heck out of that particular block to find out the speed paths that would create this problem. And at a very high level, this is my only slide which kind of gets into any details of this IFRA approach. What we do is that in the design phase, we insert these recorders inside the chip design. So you can think of, for every pipeline stage, there is a small recorder associated with that pipeline stage, which stores very specific information corresponding to that pipeline stage. And the total amount of storage that you need for these recorders overall for the alpha microprocessor chip is like roughly around 60 kilobytes and of distributed storage. And and when the post-silicon validation is happening, these recorders store special information in a non-intrusive way, because you do not stop the system or anything. It's happening all in parallel. And when a failure is detected, that's what is important, because you want to detect the failure fast. Now, if the error appeared, a billion cycles from the beginning of your execution of validation, you don't care about that. What you care about is the appearance of the error to the appearance of the failure. So that's what you want to make to be, you want it to be very short, and that's where some of the error checking techniques play a very special role. Once the failure is detected, you scan out the contents and you post-analyze offline using some special analysis techniques. Actually, we use some ideas from fault tolerance literature on control flow analysis, data dependency analysis, and so on. You can think of using compiler theory basically to do diagnosis basically. And you do not need any system level simulation, because we are looking at self-consistency. We knew the assembly code or the binary of what you were running in the post-silicon validation platform, and we have this information from the recorders, and we look for self-consistency, that whether things are consistent. If you read something, like if you wrote something, whatever you read was the same thing that you wrote, and so on, and to be able to localize these bugs. Again, 2,000 feet view of the thing, but does work in real life. And as I said that, we also do some work beyond CMOS. This is blue sky stuff, on designs with carbon nanotube field effect transistors, they have a big promise. The energy delay benefit of using carbon nanotube FETs could be around 14x or something like that, at least 10x. Okay, so somebody said in a company said if you guys tell us 10x, and then after all the work is done, probably it will be 50%, but still we'll be very happy about it. So that's why you have to start off with a big number, and 10x is true. But there are some major showstoppers. You cannot grow these carbon nanotubes parallel to each other. Like you can look, these are carbon nanotubes. Oh, okay. What are carbon nanotubes? Good. So carbon nanotubes are very simple. You have graphene, okay? You have a sheet of graphene. And what is graphene? Well, graphene is a very fine sheet of graphite. And what is graphite? The stuff that you use in your lead pencils, basically. So if you draw a line, or if you shade a region, you get multiple layers of graphene, basically. And so if one of those layers of graphene you could get out, and then if you rolled that sheet of graphene, you will get a tube, and that is what a carbon nanotube is, basically. Okay. So So what we do is that you can grow carbon nanotubes either on silicon or on quartz. Okay. Now we have found that these carbon nanotubes grow better on quartz than on silicon. I have some pictures on carbon nanotubes on silicon. It will see that it will really look like noodles. Okay. Versus here, as you can see, that they kind of look like kind of straight with some kinks and bends and so on. And we can grow actually on full wafer scale and so on. Now, if you want to make logic out of these carbon nanotubes, as you can guess that if things go left and right, how in the world can you design logic that would ever work, isn't it? And so you have to worry about mispositioning of the carbon nanotubes. They can be misaligned. You cannot tell that I want a carbon nanotube here, I do not want a carbon nanotube there, and so on. You have to deal with that problem. And oh, by the way, roughly around a third of the carbon nanotubes turn out to have zero band gap, which means they act as metal, which means they're always conducting, which means if you are creating transistors out of those, you will have source drain shorts, basically. Given all these things, you want to make a real technology out of these things, okay? And we haven't solved the problem. I'm not saying we solved the problem, but we actually had the first VLSI scale demonstration this June at the VLSI symposium, where we could do full wafer scale growth of carbon nanotubes. And we were growing them on quartz because they have better alignment behaviors on quartz. But no one wants to use quartz for doing circuits, isn't it? So we can use a sticker technique actually to pull the carbon nanotubes out of quartz and put them on silicon. We can do that actually. And then after doing that, we actually have a theory based on graph theory, where we can prove that no matter how misaligned the carbon nanotubes are, as long as they are directional, which means they are not spiraling in one particular place, actually there is a way to create layouts of logic circuits so that even if the carbon nanotubes are misaligned and mispositioned, you will always have correct logic functions no matter what. And these are some examples of those. This is a pull-up of a NAND gate, this is a pull-up of a NOR gate, and you can see look at the currents, they actually work in real life. These are some more complex gates, like this is an AND-OR invert and OR AND invert and so on. So we are at least there, where we can create single logic gates. And like we are working on more stuff as we speak.
So this VLSI chip was synthesized in Stanford lab?
Well, it was created at Stanford lab, yes, exactly. It was fabricated at Stanford lab, yes. Yeah. So those are some of the other projects that are going on in our group. And I did some other stuff too, before I joined Stanford, basically. Like I like to do stuff, basically. It doesn't really matter what it is. So this was basically, as I said, I was talking about this coding theory thing, that we developed, basically. When I was at Stanford, I went to Stanford for graduate studies, basically, for my PhD. And we did a lot of stuff. We worked on these self-repairing FPGAs. We had this big project on reconfigurable computing, where we were saying, well, if you have permanent faults, you create another configuration that avoids that particular location of the fault, and still you can continue to run your application and so on. We showed all that stuff. And then we also did pure software techniques for hardware fault tolerance, basically, and that were deployed on the Argo satellite up in the space, and that actually sent data on what kinds of soft errors happen up in the space, basically. And they had a radiation hardened microprocessor, and they had a commercial microprocessor with no hardware fault tolerance. And with the software techniques, the commercial processor did better than the radiation hardened processor. And like there were lots of interesting stuff basically in that space. So that kind of concludes my talk. I hope that I got the message across that going forward for robust system design, there are lots of challenges, but there are lots of new opportunities that are either created by understanding the physics or because of changing cost constraints in future technologies. But that means that we have to think of new ways of doing things. And I hope what we talked about today would be bringing some sea change in future designs. So thank you very much.